So the first problem has to do with an aromatic system, but this aromatic system is not benzene. In a previous assignment, you showed that the ring of this molecule, which is called furan, is in fact aromatic because you have 2, 4, and then one of these lone pairs participates in the pi system of the ring, 6 pi electrons, a continuous, fully conjugated system of orbitals around a ring. So this is in fact an aromatic ring. The numbering of furan goes like this. The oxygen gets number 1, this carbon is number 2, this carbon is number 3, and so on around the ring. Notice that 3 and 4 are equivalent. 2 and 5 are also equivalent just by the symmetry of the molecule. So the question is, if one were to do electrophilic aromatic substitution on furan, would you expect a product in which the electrophile becomes attached at carbon 2, or a product where the electrophile becomes attached at carbon 3? And you know how to approach these problems. You need to go along each of the pathways and compare which one seems more energetically favorable. So please pause the video and see if you can determine what should be the regioselectivity of electrophilic aromatic substitution. All right, let's see how far you got. We have to start out by pushing an arrow from the aromatic system of furan toward the electrophile. Now that arrow in and of itself does not resolve the question, because it could mean either attach carbon 2 to the electrophile or attach carbon 3 to the electrophile. So really what we need to do is we need to analyze both possibilities. So let's start with the C3 substitution pathway. And then later we'll look at the C2 substitution option. So again, if you didn't get very far on your first attempt, here's another chance. Use this arrow and let's go through the C3 pathway. So over here, we just have to make sure that if we're going to try to make the product that has the new bond between C3 and E, let's put that there. Let's also include all of the other hydrogens that we started with, just making it easier to keep track of things. Here's atom number 1, 2, and 3. There's a plus charge right there. And then remember we have 2 lone pairs on the oxygen of the furan. All right? So on the other hand, if we go along the C2 pathway, you might want to try that if you haven't gotten there already. Along this pathway, we once again want to be careful to include the various atoms that we know are there. The big difference is that E will be attached to carbon 2, and the plus charge will be here at carbon 3 along this C2 substitution pathway. Now at this point, you know what to do. You have to do an analysis of this carbocation intermediate versus this carbocation intermediate. And the typical way to do this, and we'll do it here, is by drawing resonance structures of each and comparing. So try that if you haven't done so already. Let's start up here with the C3 substitution pathway. This positive charge can be resonance stabilized from the furan ring oxygen in this way, and that would generate a corresponding resonance structure of this type, where there's now a formal positive charge on the oxygen of the ring. Let's see what happens over here in the bottom case, and I shouldn't forget to put these lone pairs here, maybe that will be helpful. So let's write some resonance structures of this cation. If you look at this part here should look familiar. That's an allyl cation type of substructure within this molecule, and so we know we can do that kind of thing. So here is another resonance structure of this material, E. So that has a plus charge now on this carbon right here. And here's the difference. In this lower pathway, I have yet another resonance structure that I could write, because now I can get this oxygen involved in this way and draw a third resonance structure of this cationic intermediate. So this one also has the formal positive charge on oxygen, the H, there's the electrophile, the other various hydrogens along the ring. So along the C3 substitution pathway, we have this type of resonance stabilization, whereas along the C2 substitution pathway, we have a greater degree of resonance stabilization. So what would we predict? Well, the transition state leading to this cation should be correspondingly lower in energy than the transition state leading to this cation. So this pathway here should be favored, should be faster. You expect this path to be faster and this path to be slower. So assuming the reaction is under kinetic control, and we should make that assumption, this will be the favored pathway. We just have to finish off the reaction now. So remember, at the end of electrophilic aromatic substitution, you need to restore the aromatic ring by removal of a proton from the sp3 hybridized carbon. So find the sp3 hybridized carbon. Let's use this resonance structure here, and our base is going to be X minus. Okay? So if you didn't get a chance to do this yet, deprotonate from the appropriate place to get to the final product. Here's the sp3 hybridized carbon. Here is the hydrogen that we need to remove as a proton. So here comes the base. Take the proton, and then the electron flow would be this way, and that way. You should prove to yourself that you could do the same deprotonation from either this resonance structure or the first resonance structure and end up with the same product. So the final product has the aromatic furan ring again, except that at the position that we've numbered, position 2, there is now the E. So this is the so-called 2 product, because again, oxygen, according to the official numbering system for furans, gets the 1 and that gets the 2. The larger message here is that anytime you're considering competing electrophilic aromatic substitution processes, what you should do is to work through the various possibilities and look and see which cationic intermediate you expect to be formed most readily or more readily, and that is the pathway that you would expect to be preferred.